Okay, I would just like to apologize in advance for how terrible this video is. I did not have my normal video making software at home, so I am making do with my cell phone. So, this video is going to be on derivatives of trig functions. And so first what we're going to do is we're going to write down what the 6 different trig functions are. And then we're going to write down the derivative of each one of those. And let me see, zoom in a little bit more. Okay, so the first trig function we're going to look at is sine x. We're also going to look at cos x and tan of x and cosecant of x and secant and last cotangent. So for the first one, the derivative of sine is cosine. The derivative of cosine is negative sine. And I am sure there are proofs somewhere for all of these, and if you really need to, we can look at those and see where they came from. But for the most part, we just memorize them, and then we use them. The derivative of tangent is secant squared. The derivative of cosecant is negative cosecant x, cotangent x. The derivative of secant is secant x, tan x. And the derivative of cotangent is negative cosecant squared x. Okay, so the first problem that we're going to do is we're just going to find the derivative in a few different circumstances. So the instructions would say find the derivative. And for the first problem, we're going to find the derivative of the function x squared minus 1/2 cos x. So this is one of those problems where you can kind of use properties and we can say, oh, let's find the derivative of this piece first, then we can find the derivative of that piece. So the derivative of x squared is 2x. And then we know the constant rule tells us that we can keep that 1/2 just in the front. We're just going to look at the derivative of cos x. And the derivative of cos, like we said, is negative sine. So that means that y prime is 2x plus 1/2 sine x. All right, for our next example, we're going to look at the derivative of y equals sine x tan x. And this is actually a picture of the product rule. So we've got two different things that are being multiplied together. And so we're going to do the product rule with this. So I'm going to say the first one multiplied by the derivative of the second one, and the derivative of tan was secant squared, plus the second one multiplied by the derivative of the first one, which was cos x. And this is where we have to consider whether or not there are any properties, trig properties here, trig identities here that we could use to simplify the problem a little bit. So sine x secant squared x, that's not going to change at all. We're going to keep that. But I know that I can rewrite tan as sine over cos. And if I'm multiplying that by cos, then the cos on the top and the cos on the bottom would cancel out to make a 1. So I can say the derivative is sine x secant squared x plus sine x. I don't know if you guys can hear it, but my cat is madly batting around a little piece of wire. It's distracting. All right, last example of this sort. We're going to say our original function is f of x equals x times sine x plus secant x. So we're going to use the derivative rules here as well. this x sine x is again a product rule. And then with this one, I'll be able to just do the derivative of that piece and be good. So I'm going to say for my overall derivative, I've got the first times the derivative of the second one plus the second one times the derivative of the first one. And so that takes care of the x sine x part. And then the secant x part, I'm just going to look up here at my little shortcuts here, and I know that secant would be secant x tan x. And then I can go through and kind of simplify that. So I've got x cos x plus sine x plus secant x tan x, and that is my derivative. All right, we're going to do another type of example. This time we're going to find the second derivative of f of x equals x cos x. So, of course, we have to find the first derivative first, and as you can see, this is a product rule. So I'm going to do the first one multiplied by the derivative of the second one plus the second one times the derivative of the first one. And so that means that my first derivative is negative x sine x plus cos x. And then for me to find my second derivative, I've got a product rule right there, so I'm going to have to do that again. So I'm going to say the first one multiplied by the derivative of the second one plus the second one multiplied by the derivative of the first one. And then I have the derivative of cos x on the end, so I've got plus and then negative sine x. And again, I've got some simplifying I can do before I can conclude what my second derivative is. So overall, I would say my second derivative is negative x cos x minus 2 sine x. Okay, and we have one last example. We're going to say, where does f of x, and this function is defined as secant x divided by 1 plus tan x, where does it have a horizontal tangent on the interval from 0 to 2 pi? So the first thing I want to make sure that I know is that a horizontal tangent means that the slope there is going to be 0, and tangent lines are lines that are right next to the curve, right? So we're going to be looking at the instantaneous rate of change, and we know that that needs to be 0. And so really what we're looking for here is we want to know where the derivative equals 0. So the first step in that would be to find the derivative. And since our original function is a quotient, we have to do the quotient rule. So we're going to say low d high minus high d low, if you guys remember that. So the bottom times the derivative of the top, and the derivative of secant was secant x tan x, minus the top times the derivative of the bottom. And the derivative of the bottom, the derivative of 1 is just 0. And then the derivative of tan is secant squared. And then all of that is divided by the bottom squared. Okay, so we're going to go ahead and simplify a little bit. So I've got secant x tan x, and then plus secant x tan squared x, minus, when I distribute that I get 0, and so then I've got secant to the third x, so that's the derivative. And I'm trying to figure out where the derivative equals 0. So the nice thing about fractions is that if you want to know when a fraction equals 0, you just have to make the top equal 0. So long as it doesn't make the bottom equal 0, so we're going to have to check our answers at the end to make sure they're okay. So what I'm going to do is I'm going to go ahead and just take the top and set it equal to 0. And typically when we have things like this, we've got x squareds and stuff, we're going to go ahead and factor that. And if you notice, there's a GCF of secant x. Secant x shows up in all of those pieces. All right, so you might stare at that for a little bit. At this point, this secant x is able to solve. We can solve that. We are just going to take that factor, set it equal to 0. Over here, we want to keep factoring this, and the only way we're going to be able to keep factoring it is if the entire thing is in terms of tangent. And so I know that secant squared is the same as 1 plus tan squared, so I'm going to go ahead and replace that. And then I can go ahead and distribute that negative, and what I notice is it gives me negative 1 minus tan squared x, and then this tan squared and this tan squared cancel out. So now in this factored form, I just have secant x times tan x minus 1 equals 0. All right, so now I can go ahead and solve. I can say I'm looking for where secant x equals 0, and I'm looking for where tan x equals 1. So secant x equals 0, if we look at our unit circle, that's going to maybe be a hard time for us because we think of things in terms of sine and cosine and tangent. So I'm going to say that secant x is actually the same as 1 over cos x equals 0, right? Because secant is the same as the reciprocal of cos. And so if we look at this, you'll notice there is no way for this fraction to equal 0. We've got a 1 on top. And the only way for a fraction to equal 0 is for the top to be 0. So this is not possible. There's no solution here. But over here, we can find values that would make tan equal 1. So if you're looking at your unit circle, you're going to look, because tan is y divided by x. And so we're saying we want to find the angle where the y divided by x equals 1. So we're looking on the unit circle where the x and the y values are identical. And that happens in 2 spots. It happens at pi fourths, and it happens at 5 pi fourths. So there are 2 solutions to this problem. So pi fourths and 5 pi fourths. And just to make sure that we are kosher with this answer, we do want to go back, because this was a fraction. We do want to go back and we want to make sure that if we plug those values in, we're not making the denominator equal 0. And we know that we won't, because we solved where tan x equaled 1. So we're going to have 1 plus 1 on the bottom of our fraction. That's going to be 2. And so we know that these answers are not extraneous. These answers do work. So the 2 places where we're going to have a horizontal tangent is going to be pi fourths and 5 pi fourths. And in theory, you should be able to plug that in your calculator. If your calculator is in radians, you should be able to plug that in your calculator and verify that you would see a maximum or a minimum on the graph there where a horizontal tangent would make sense. Okay, one last example. We're almost done. We're going to find the 27th derivative, oh my gosh, of the function cos x. All right, so for us to understand this problem and not think that our teacher is evil, we're just going to look at some derivatives. We're going to see what's happening here, because hopefully you're recognizing, like, but the rules, cos went to sine and sine went to cos, and that could be an interesting thing to look at. So the first derivative of cos is negative sine. And then the derivative of negative sine would be negative. We're going to keep the negative 1 in the front, but the derivative of sine is cos. And then after that, you'd be like, okay, well, now I'm taking the derivative of cos again. The derivative of cos is negative sine. So we've got negative of negative sine. That gets you back to positive sine. And then the fourth derivative, the derivative of sine, is cos. It gets you back to the original problem. And then you circulate through this. So we could say first derivative, second derivative, third, fourth. And then fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. So if you're noticing, every time we go through 4 derivatives, we've gotten back to the original problem. So what we're going to do is we're going to say if I take 27 derivatives and I divide it by 4, that's telling me how many times I'm going to cycle through those 4 derivatives. So I know that 27 divided by 4, it goes in 6 times evenly, but then we've got 3 leftovers, right? Because 24 divided by 4 is 6. So 27 divided by 4 would be 6 with 3 leftovers. So remainder 3. So I'm going to say remainder 1 would be here, remainder 2 would be here, remainder 3 is down here. So the 27th derivative, oops, I wrote that wrong. The 27th derivative of cos x would be sine x. And we figured that out by being tricky.